Hello, my name is Musawir Ahmed Khan. Today I will be taking you through one of the topics in our course outline for ENEL 327. This is the first of four modules that will explore the topic of discrete signals and their properties. This module will give us a basic understanding of discrete time signals, their properties, and some of the operations we perform on these signals. We will explore many applications and uses of these signals, and as a result, we will also have to learn more about their properties, linearity, and time invariance. In addition to these properties, we will also learn about impulse signals and convolution. This module will employ, after covering each topic, we will analyze them mathematically as well to solidify our understanding of these concepts. Before diving into discrete time signals, let us first revisit continuous variables and continuous time signals. Continuous time signals are nothing but a stream of values that were measured over a continuous period of time. Let us consider this simple distance against time graph, where we can see that an object was clearly started moving from t equals 0 and then continued over a steady pace until this point where it remains still for two more time periods before starting to move again. In this kind of in these continuous signals, we are able to know exactly what is going on in between these points because we can calculate the gradient of suppose this portion of the graph and find out exactly what was happening right here or anywhere in between. However, in contrast, if we think about discrete signals, they are quite the opposite because discrete signals are just a certain number of values sampled over a certain period of time at constant intervals. Now, to break that down, what we mean is these values they are equally spaced apart and they were recorded at certain intervals of time and they were used to reconstruct our older signal. Now, what is different between this and a continuous time signal is that there are no values in between these time intervals. Now, let us think of this mathematically. Say x of t was the original continuous time signal we drew before, then that could be modeled as a discrete time signal like this, where x is a function of n times ts, where ts is one interval between each recording. So what we can say is the discrete signal is made of n number of samples sampled over time intervals ts. Now, you must be thinking, why do we bother studying about discrete time signals in the first place? Because they do not have any values in between them, right? So surely they are not as useful as continuous time signals. Yes and no, because discrete time signals are used by everything we can see around us, whether it's the YouTube videos we're watching or the Facebook posts we're liking. Here we can see two graphs that portray the difference between continuous and discrete time signals in more detail. The first graph here is a graph of a recording of values that were taken over 32 milliseconds. However, in this graph, we can see that it is the equivalent of the continuous graph, but it consists of 256 samples taken after equal intervals over the same period of time. Now, maybe you are wondering, why do we bother studying about discrete time signals in the first place? Because they are missing values in between each of their little intervals. Now, that is a very good question. Discrete signals are present all around us. They are used to compute all the regular things that we are used to seeing in our daily lives. Everything uses discrete time signals because they are a much more efficient way of analyzing various signals and data. To find out more about why these signals are so useful, we will delve deeper into two of their properties: linearity and time invariance. A system is said to be linear if it obeys the principle of superposition. The principle of superposition can be broken down into two further properties, which are homogeneity and additivity. We will discuss both these properties in more detail in the next few slides. Here is a basic portrayal of what linearity means in signal processing systems. Here we can see that if a system has two inputs and they are scaled by a constant alpha, that would be the same as two system outputs added after being scaled together. To put this more into perspective, let us break this down. Now, for homogeneity, according to this equation, we can see that homogeneity means scaling the input of a system by a constant should be the same as scaling the output of the system to that same input. So here our input is the signal X and our output is the output of the system for the input X. Now what we can see here is when we multiply the input X with the constant A, that has to be equals to multiplying the output of the same signal with the constant alpha or A. Moving on to the second property of superposition, additivity. Additivity states that if a system has two inputs, then the output will be of the individual the sum of the individual outputs of the two inputs. Here, if our two inputs are x1 and x2, then the output of these two inputs should be equal to the sum of these two inputs x1 and x2 separately. Now, if we go back to the initial slide, you will see that this diagram is starting to make a lot of sense. Let us walk through this once again. So here we can see the principle of homogeneity, where we are scaling x1, the two inputs x1 and x2 with two constants alpha 1 and alpha 2. And we are adding them together and putting them through the system to get the output yt. Now you can see that this is also equals to inputting these two inputs into the system, scaling their outputs here, and then adding them together. So y1 and y2, their sum is also equals to yt. So here we are seeing the property of homogeneity, and here by comparing these two systems we can observe the property of additivity. Now that we have learned more about linearity, let us move on to the second property of these systems, time invariance. Time invariance means that a time shift in the input of a system results in the same time shift in its output. So let us suppose that yn is the output of a system with the input xn. So if the system were to be time invariant, introducing a delay in the input of the system should result in the same delay in the output of the system, as we can see here in these two diagrams, where we are putting in the input before, we are putting in the input after adding a delay, and then we can see that we are adding a delay after we get the output from the system, and they both result in the same output yt minus tau, where tau is the constant that we are shifting the signal by. this is all we have for this module. In the next module, we will be learning about impulse signals and how they are used for one of the most important operations in discrete time signals, convolution.